remaining minute that we don't have, H of P is concave in P. So P is a probability mass function. So H of P is minus summation Pi log Pi. And we are trying to show that H of lambda times one distribution plus lambda bar times another distribution. This is called the mixture distribution, has some inequality relationship to lambda H of P1 plus lambda bar H of P2. All right. Okay. Now, that's what we're trying to prove. But notice, if we set up the following problem, let x1 be drawn according to P1. I underbar it because it's a probability mass function. It's a vector. X2 is P2. And I define x theta to be x1 with probability P1 and the random variable x2 with probability P2. So I have two experiments. I perform one, I generate x1 this way. I generate x2 this way. But before I look at the outcomes of the experiments, I flip a theta coin, and this is not P1 and P2. This is lambda and 1 minus lambda. I flip a lambda coin to determine which experiment to look at. Hot gas, cold gas, lukewarm gas. It's a mixture of the two. So the entropy of the mixture is greater than or equal to the mixture of the entropies. But, and now since we are over, I will just state right here what this is. This is H of the random variable x sub theta, because that's the distribution I get when I do this compound experiment. And this is lambda, well, H of P1 plus lambda bar H of P2. It's, if you wish, it's H of x given theta. So this is really just the concavity of H of P follows immediately from the information doesn't hurt inequality, because this entropy is greater than the conditional entropy, and we've set up the problem that way. We can prove a lot of classical inequalities that way, having to do with determinants and this and that and the other thing. Later for that. Okay. Next time we'll do some things. Maybe we'll do the AEP.